Welcome to the What's New in Autodesk Simulation Mechanical 2017 webinar. My name is Sualp Ozel, and I am the product manager for Autodesk Simulation Mechanical.
My name is Marwan Azam, and I'm a technical support specialist working with Simulation Mechanical and CFD.
In this presentation, we will highlight some of the new functionality in Autodesk Simulation Mechanical 2017. When we started our planning for this release, we had three focus areas, and these are the main areas for the 2017 release. In the 2017 release, we added advanced Nastran support, enhanced usability and meshing improvements, as well as improvements in our results evaluation. So let's get started.
All right.
So the first key focus area for us was the ability to control the Nastran parameters. So as we look on the left-hand side of this screen, we see that we now have full control over all the Nastran parameters for a static stress with nonlinear material models analysis type. We added a brand new tab in the analysis parameters dialog specifically for controlling all the Nastran parameters. With this dialog, you are able to control things like whether you want large displacements on or off, or any kind of different tolerances for different types of contact and stability factors.
So basically, these are Nastran parameters that were already there, but we didn't have the access to them through Simulation Mechanical, and now we do.
Exactly.
And that first screen capture on the left shows the analysis parameters from a nonlinear analysis, and the one on the right is?
The one on the right is around contact controls. So if you look at the picture on the right, you will now see that within the Simulation Mechanical's user interface, we have a unified dialog that controls the Simulation Mechanical contact settings as well as the Nastran contact settings. And we'll demonstrate all of this with different models right now. So let's go into the software, and Marwan will drive the software and give us an overview of what we're looking at. So first model we're going to be looking at is the traction gear. In Simulation Mechanical 2017. So here we're looking at the, let's start with the first design scenario with Nastran static nonlinear, Marwan, and load it up.
All right, so what we have here is a two-part assembly. It's set up as a linear static stress analysis, or static stress with linear. Actually, this one is with nonlinear material models. Okay, and the first thing you see is this.
The first thing we want to do is go to Setup and highlight the fact that for static stress with nonlinear.
That's what we saw in the actual slide a minute ago, is that we added this Nastran tab that allows us to control these Nastran contact parameters.
Yeah, and this is specific for static stress with nonlinear material models. The next improvement was around contact. So to demonstrate that, we'll go into the second design scenario, which is our linear static stress design scenario.
What we did here is previously under parameters you had the contact tab. We took that out of the analysis parameters dialog. Here you used to have a contact tab. We don't have that anymore. In fact, we made it easier by putting it in incorporating it in the model tree. So if we right-click on that and click on Edit Settings, we have the surface contact, and we had those before in that tab, the iteration method, the number of iterations, and so on. You can control those here. And the second tab is the smart bonding. That was not its own tab, that was just an item under that old tab. You can enable or disable the smart bonding. And for those of you who don't know what smart bonding is, regular bonding and a linear stress analysis works off of the matching between two parts. So you have to have identical meshes on the two parts so for them to be bonded together. Smart bonding does not require you to have matching meshes, even though you do need to have the meshes touching each other, but you don't have to have them matching. So you can have different meshes on the different parts and still use bonded contact between them.
And it works for bonded and welded contact.
That's right.
So that was the first improvement, is to eliminate the contact tab from the model parameters. And the second one was the addition of full control over Nastran contact parameters. So depending on what type of contact you're trying to control, if you right-click on it and go to the Edit Settings, and here we're controlling the default contact between all the parts, simulation mechanical contact options can be controlled, as well as with the drop-down, you can switch to control the entire Nastran contact options. For those of you who know Nastran pretty well, we also added a reference to which specific Nastran card you're about to control in parentheses. So in this case, we are controlling the Nastran card called Contact Generate. And you can control its contact type to be welded or offset welded. And these two are keyed off of the type of contact you have picked in the default contact in the tree. So if you had chosen surface contact, for example, you would have a different list of contact types. So another thing we did is also control the contact type and contact settings, not for the default, but for the explicit contact pairs. So Marwan just right-click edited the surface contact pair between Part 2, Surface 7, and Part 1, Surface 14, which is highlighted in the tree right now. And he showed us the settings for Nastran, and here we're seeing in the parentheses that this is controlling the Nastran contact card called BSCompE. And now, as you can see, the contact type is called General, and you have the ability to control whether this is a general symmetric or general unsymmetric type of contact. And when you do, you have things like contact coefficient of friction enabled. A moment ago, when we were looking at bonded contact, the coefficient of friction field was grayed out. So this dialog has a lot of logic in the background that enables and disables things that are applicable to the type of contact you're adding. We also added the description field on the bottom. So for those of you who like to rename your contact pairs, you can type in a quick description. So let's type something here and call maybe test 123 and see the effects. And when we hit OK, what you're going to see is the name for the contact pair will be changed to whatever it is that you named. If you want to go back and delete that in the Edit Settings dialog, it will go back, the description will default back to the part number and surface number combination. So when you hit OK, it will automatically default back to the part and surface number combination. So this is the improvements to linear static stress and how we control contact for simulation mechanical and Nastran solvers. Now let's move on to our third design scenario, which happens to be MES, mechanical event simulation, and highlight some of the improvements to contact settings for a more complicated analysis type such as MES.
And just to add one more thing here, it's basically the same idea where you have a default contact, which can be bonded or any kind of contact, and you have separate contact pairs, and you can have any kind of combination, but you can also control, have, this could be any one of them. They of course have to be either SimMech or Nastran for everything. You can't mix and match SimMech or Nastran, but you can still, like before, mix and match what kind of contacts you have between the different pairs and go into the settings for each contact.
One thing I forgot to mention, let's access the settings for a surface quickly and hit Edit. While we were looking at the Nastran settings, I mentioned that contact could be symmetric or unsymmetric. And we didn't really get into the description of this, but a quick description for an unsymmetric contact means there will be a master surface and there will be a slave surface in a given contact pair. And the calculations take a lot less time if you choose the unsymmetric, because the solver only needs to find out the relationship between the master and the slave, and not the other way around. Now, whenever we choose unsymmetric, we also have to tell the software which surface is the master and which surface is the slave. And the way we do that now is the first surface that we see in the description becomes the master, and the second surface that we see becomes the slave. So in this example, it would be part 2, surface 14 is the master, and part 1, surface 8 is the slave. And of course, we need to be able to control that. If you hit OK to this dialog, Marwan, we also added the ability to switch the master and slave by flipping which one is the first and which one is the second. And that's simply in a right-click menu called Flip Primary and Secondary. So as you can see, we added the capability to flip the primary and secondary. We also have the capability to copy the settings, the entire settings, from one pair to multiple pairs. So on that right click again, we have the Copy Settings dialog. And if you click it, it copies it. And then you can select one or multiple pairs. And using Shift or Control keys, you can select multiple pairs. And you can say Paste the settings, and it will paste all the settings, such as your friction coefficients and max activation distances and so on and so forth, to other pairs, which makes it very easy to define your settings for one pair and copy paste it to multiple pairs. With all of these improvements, we had a chance to touch the MES surface contact dialog and make it much better as well. So let's go ahead and load up that design scenario and talk about some of the improvements here, Marwan.
All right. So again, so now you see that the analysis type is MES with nonlinear material models. And we have the same basic thing where you have a default contact and individual contact pairs. Previously in version 2016 and before, if you had nothing selected on the screen or canvas and you right-clicked, you would get an item that says General Surface to Surface Contact. That has been taken out of here.
It was also on the ribbon as well.
It was also on the ribbon, General Surface Surface Contact. That has been taken and incorporated now in the browser. And that's General Contact Settings here. If I right-click and I click on Edit Settings, I get the kind of things that I had there. I mean, that screen, the General Surface Contact screen, was a bit complicated. It had many things. It had a table that showed you all the contact pairs. It had enable and disable a certain contact pair and so on, including also this contact element updating that was at the bottom there, which allowed you to choose whether you want to automatically update or never update, or at a certain frequency. That is now over here. And instead of the table that shows the contacts, now we have them all listed under the contact pairs. And again, now if I right-click and go to Edit Settings, that's going to look a little different than, say, a linear static stress contact setting. That's the kind of thing that you had to click on Settings and again on Advanced and the General Surface Contact. This makes it cleaner and simpler. So you can select any surface contact pair and go to the general, whether it's surface contact or sliding or tight contact. Under Advanced, you get low speed, high speed, the contact stiffness, whether it's automatic or user defined, the contact distance, also whether it's automatic or user defined, geometry, the contact interaction distance, maximum penetration distance, and the extent contact element size, and the time step tab. So it's basically all the parameters that you had, but they're laid out a little differently, more logical and cleaner looking and easier to access here.
Let's go back to the general quickly, Marwan. This dialog is an interactive dialog, and it actually expands in size based on the things that you have selected. So Marwan selected include friction, and as you can see, the friction tab became available. It wasn't there before. Whereas in the 2016 version, all these options were always visible, and therefore the dialogues became really large and complicated to look at.
Same thing would happen if you had the contact defined between plate elements. You'd have the side of plate element, or if the contact was defined between beam elements, you'll also have the appropriate parameters shown, whether they're used or not. Now, it recognizes if they are, it will only show it to you if that is the case.
That's right.
So hence, more cleaner look.
And that is pretty much the end of the improvements for all the contact settings. Let's move on to the next slide, which is around our enhancements to our usability and meshing capabilities. So let's talk a little bit about our usability enhancements first. The first thing that we did is we added a method where you can interact with plate elements and control the information such as thickness or element normal point interactively when you're dealing with a static stress with linear material models and plate elements.
Yeah, so let's bring up a model that shows that here. We're going to go to the software, file open, go up one folder, go to the plate elements, and let's look at this model. It's a model of a grill. Obviously, it has many parts, but for our purpose here, we're just looking at part 74, which we set as plate element. And I'm going to rotate this model so that I show you where this part is. So that's the back panel of the grill. That's our part 74.
47.
47, I'm sorry. So we can, that's this part over here.
And let's isolate that by right-clicking.
Go up here, isolate, so we're only looking at this part. So the model was set up just with this part, and those edges here, actually it's a bit more than you see here. There are edges to it, like that. And these are fully constrained. Anyway, that's not what we wanted to show you. What we wanted to show you is more in the element definition.
So this model, this part that we're looking at, is actually a solid object, and it was meshed using the midplane meshing technique. So as you can imagine, a solid object will have a lot more surfaces than a midplane plate version of that same object. So in this case, this had, Marwan is trying to show us, it had roughly 200 plus, so it looks like 212 surfaces as the original solid object. And when we midplane meshed it and called it a plate element, it has a lot less. And we can control the thickness of all these different subsurfaces that make up this plate element if we wanted to. And to do that, we would normally have to change the element definition so that the properties are based on either part-based or surface number-based. So by default, Simulation Mechanical gives you a part-based description, and you have to enter a certain thickness and a certain element normal direction, which will help you apply things like pressure, like an internal pressure or an external pressure in the case of a pressure vessel. So here, in the past, we would have to change our properties between a part-based to surface-based directly in this element definition screen. In 2017, we added the capability to do that outside of this dialog as well by simply right-clicking the element options in the tree. So let's go ahead and cancel this for a second and show that option, which is right under element definition. We have element option. So this is a new entry that shows up for plate elements in static stress, which lets you change from part-based to surface-based. The second thing is once you have a surface-based input option, you get an entire list of surfaces in the element definition. And you can see that the surface numbers kind of jump around. In this case, it jumps from 2 to 15 to 18, and it goes all the way down to a potential 212 in this case. So this is a subset of those original 200 plus surfaces. And this list is kind of difficult to manage when the number of surfaces gets bigger and bigger and bigger, especially if you want to control the thicknesses for different groups of surfaces. So this was a big problem that you guys, our users, reported to us. So to eliminate this issue, we added the ability to interact with those surfaces directly on the canvas. So let's go ahead and hit cancel, Marwan, and pick a couple of surfaces, especially around these openings. So
I'm going to pick this surface. Of course, these openings.
Let's pick a couple.
Okay, let's maybe pick these three here.
Perfect.
And we can right click and go to Edit, Element Definition.
So this is brand new.
That's a new item. So now we're only editing the element definition of those three surfaces. And it doesn't give you the surface number, it's just the same parameters for all three of them. So it doesn't matter what the surface number is, you're going to set the same, but by the fact that you selected all three of them at the same time, that means you want to set the same parameters for all of them. So let's say that's 0.05. And we can pick an element normal point. Previously, you had to know the coordinates of the element normal point, and again, like Sualp said, the element normal point helps you decide which way the pressure goes, and it decides which side is the bottom, which side is the top of the element. And previously, you had to know these coordinates and type them in, which can, in many cases, be a little painful to determine all these locations. Now you can click on Pick and graphically pick a node or a vertex on the model, and that will be your element normal point. Let's say you just wanted it to be inside this, a node like this, a vertex like this would be good enough. And of course, if you wanted to change one of the coordinates here, you can go ahead and do that. Let's say you wanted to make the x 0, let's say, or -10. You can just do that and hit OK. So it sets the normal point as such. And if we now go into the element definition of the entire part, we should be able to see those three surfaces here have changed. There you go.
And the other thing that we did, another feedback we received from our customers was the ability to use the part-based properties as a starting point for surface-based properties, because most of the time you guys are creating plate elements, a model that has plate elements, and most all of those surfaces will have the same exact thickness, element normal point, except maybe 2 or 3 of those subsurfaces will have something different, much like what we just did here. So when you switch from a part-based to surface-based, we now get a question, a dialog that says, do you want to use what you have defined? So let's change the thickness just to demonstrate this from 0.065 to, let's say, 0.1, just as a random number. And then hit OK. And then go back in there and change it to a surface-based. And when we change from a part-based to surface-based, the question will come up and says, hey, do you want to copy and paste all those inputs as a starting point? And this option didn't exist, so most of the time our users would start with a certain thickness and element normal point, but then they would get, when they changed to a surface-based, they would lose all those inputs, and they couldn't use them as a starting point. Another feedback we received during our beta testing period was, what if somebody enters the thickness and the element normal point and the nodal order point, for example, for a given surface, and they wanted to copy and paste those settings into other surfaces as well. So let's do a quick test and just type some numbers in the thickness just to change it up to, let's say, 0.5. Right? And then what if they wanted to copy and paste those settings from that row to the other rows, much like they would do in Excel? now they can use the checkbox all the way to the left-hand side and copy that row. And once copied, they can pick other rows. So let's say just pick 27 and 33, for example. And then they can paste the information directly into those rows. So this is a piece of technology we didn't have before either, which was making it very difficult to copy and paste information from one row to the others.
You could, but it was a bit more tedious. You had to highlight them and right-click on them and so on. This checkbox allows you to click somewhere else and not lose your selection and so on.
I think that's enough on the plate elements selection. So let's go ahead and talk a little bit about our usability enhancements to the inquiring of results. So the next improvement that we did to our usability is around inquiring multiple results with a single modern user interface. This technology was rolled out on the 2016 release as a part of our App Store release around maybe mid-year. We got a lot of feedback and improved it, and finally now it is included with the 2017 release directly into the software. And let's go ahead and show the software and demonstrate some of this functionality.
So this analysis has been run. We're just going to go into results here and say, yes, let's look at the old results.
So historically, whenever we want to look at results, we have the ability to change the result that we're looking at on the canvas. So if you wanted to look at displacement, we click the displacement magnitude. If you want to look at the x displacement, we can select the x option. If you wanted to look at stresses, we look at the von Mises stresses or stress tensors. So let's look at stress tensor XX, for example. And here we are looking at a contour of stress tensor XX. And if we wanted to find the value of the stress tensor XX at a given point, we can select that point and right-click and inquire. Another method is go into the Results Inquire tab and click on Current Result. That would tell us the stress tensor XX at that point. So if you scroll all the way down, you would see the current result value for that single point. Now we're only looking at stress tensor XX. What if we wanted to find out stress tensors XX, YY, and ZZ, as well as the other three, the XY, YZ, and ZX? To get a big table that has all 6 outputs, we added this new functionality called Other Results Inquire. So if you close that dialog and go to the Other Results in the ribbon, which is 2 down from the current results, we have these 5 options that are available to us now. So we can say stress tensor at that point. So let's access the stress, and this is an interactive dialog, which means you can bring the dialog up and then select the points that you are interested in. And here we show you, let's just pick 1 or 2, or just 1 is good enough really. Here we show you the node that you have selected, the part that node belongs to, the x, y, and z coordinates of that node, as well as its stress tensors x, x, y, y, and z, z, and the others as well. Now the reason why we're showing you 2 rows of information for a single selected point is because you have a top and a bottom for a given plate. And as you can see, we also incorporated the smoothing options directly into this dialog as well. So you are looking at the smoothed results for those nodes. If you uncheck the smoothing, you will be able to see a lot more, because that node that Marwan selected actually is shared between multiple elements as well.
In this case, it's 4 elements, and that's why you see 8 rows. You get 2 from each.
We also added a little bit of statistics at the bottom. As you can see, you have the minimum and maximum value also shown. If we were looking at things like reaction forces, for example, so let's go ahead and do that. Maybe you can't close this dialog and choose reaction force in moments, the top one. So here we're looking at, and let's pick one of the points along the edge where we have a boundary condition.
Let's make sure Okay, this one.
Perfect. So, and a single node is not really what we want. We want an entire surface, for example. So let's change our selection style to a surface and just pick that entire surface. Perfect. So now, with one click, we were able to select many, many nodes, and we can quickly take a look at the reaction summations of the reactions in the x direction, the y direction, and the z direction for that collection of nodes that we have selected on this plate.
So in this case, if we want to select all three surfaces that have the boundary conditions, and we get the total
reaction force. Perfect.
Which our applied force is 10 pounds in the x direction, and under sum here you can see that we got that. So that's basically all the nodes that have non-zero reaction forces. And they're summed up. Not only can you look at this table here, you can do a couple of things with it. You can either save values or just save it as a text file for you to further manipulate if you want in something like Excel or something like that. Or you can also save it to the report, which will include this table and the report. So if I close this and go to report, let me just refresh the report here. Actually, this might have been added from before. So there it is, reaction forces and moments. That table is now populated and included in your report. Just by one click, you don't have to basically mess with it.
It also has the
summary at the bottom, the maximum, the minimum, and the sum.
That's good.
So in one click, you were able to include that in your report without any further manipulation of data.
And because it's an HTML format, it's very easy to export it to any other format you want. So that's pretty much the big improvement when it comes to inquiring multiple results. Just to highlight one more time, this is for 5 different result types. We can do this for reaction forces and moments. We can do it for stress tensors. We can do it for
I just want to show that even though you can be looking at displacement, you can still inquire other results.
That's right.
So you can be looking at the displacement and say, okay, what's the reaction? You just right-click and choose that. In this case, it's going to be 0, but nonetheless.
Yeah, so it's truly an interactive dialogue that lets you look at results other than what you're looking at on the screen. But to finish the story, let's go ahead and close this dialogue and take a look at the 5 options again, just so we can reiterate. We have the other results for reaction forces and moments, internal forces and moments, applied forces and moments, and stress tensors. These are all true for pretty much any type of element. We also have the ability to do it for element forces and moments, which is true for beam elements.
Mm-hmm. But of course, you would have to be selecting elements and not nodes.
Yeah. And because we don't have beam elements in this model, that option was grayed out.
Mm-hmm.
All right, let's move on to the next slide and talk a little bit about our improvements around usability for things like Centroid Creator and our improvements to meshes. So the first one is around Centroid Creator. For the past 2-3 years, we have been improving our Centroid Creator year over year. For those of you who may have missed our improvement to Centroid Creator last year we added the ability to find the center points for edges in addition to surfaces. So in previous years, we could only do find the centroid for a given surface or a given part. Last year, we started adding the functionality to find the centers of edges, which is really important when you're dealing with plate elements and you have a hole in that plate, like a circular hole, and you want to find the center point of that circular hole. You select that edge that makes up that hole. This year, we added the capability to control the different part numbers and surface numbers and layer numbers each of those spokes are applied to. So if you look at this image here, we can easily see a quick diagram of what a created spoke set would look like. So let's assume we have two parts. Part 1 is represented by the set 1 with a hole through it, and part 2 is represented by the set 2 with a hole through it. And if we wanted to connect the center points of those circles, we could create 3 sets of spokes. The first set is called the primary spoke, and we can control the part number that belongs to. The same thing for the secondary spoke, and the same thing for the connection spoke. And let's talk about why we did all of this. It's because we wanted to be able to...
Sorry about that.
It's okay. It's because we wanted to be able to give our users an option to choose the type of element they want for each set of spokes. Typically, what you want to do when you're connecting multiple parts together like this, with this connections technique, is you want to say that the primary spokes that Marwan's highlighting right now are rigid elements, and the secondary spokes are also rigid elements, but the connection spoke is a beam element. And the only way to do that in simulation mechanical is to consider them as different parts. And now we allow you to actually create different parts and different surfaces and different layers for each of those spokes.
Previously, it will generate all these lines for you, and you had to go in and select the ones that you want to put on a different part number, which can sometimes be a tedious process and prone to errors.
And
now
also
you get it here.
Associative. So that was
True.
That was the big problem. Is if you make all those changes and then you decide, oh, I want to change my mesh size, you would lose all those changes from before.
Yeah.
Whereas in the 2017 release, with all this improvement, all the part numbers and surface numbers and layer numbers that you do that you assign to spokes are associative, which means after remeshing they are retained.
Yeah, because it's not an afterthought here, it's from the very beginning. When it goes out to create all these lines, it's using all these parameters over here.
Mm-hmm. And we'll demonstrate quickly where the Centroid Creator is in the software for those of you who have not used this great functionality before.
So here we have a 3-part model, parts 1, 2, and 3, and we're going to use the Centroid Creator to generate those spokes between the holes of these two, let's call them brackets. So oftentimes you don't want to use a solid element. You're not interested in using a solid brick elements to represent that beam that connects those two holes, and you'd want to use beam elements. And the best way to do that is to just not model that part or not import your CAD model with that part and do it right here inside of Simulation Mechanical by using the Centroid Creator, and that is under the Draw ribbon, Centroid Creator. Let me go to Select Surfaces here, and I can either click that or select surfaces before I click that. So let me click that here and select this surface and add it, and click on Connect Centroid with spokes. Right now, if I just do that, it's going to create the spokes inside this hole and the centroid and put them by default in part number 5. And as Sualp mentioned, that is totally under your control. You can change the part number, the surface number, and the layer number to whatever you want. Let's give that what it is here. Right now, I can create centroids between 2 sets. So if I do that here, I can select this surface and add that as my set 2. And the reason we call that set and not surface is you could have selected nodes as well, or edges. So we keep it general, edges, not nodes. We keep it general and we call it set, right? So this is basically the dialog we were looking at in the slide. So we can change that to part 6 and 7. Yeah, 7. And we can just go back to 1, 1 here. We don't need to increment that. Actually, what it did is, by default, it put them all on the same part number and different surfaces and layers. And even if you do that by mistake, it still is, you can go back and change it, or it makes it easier to select those surfaces and put them on different part numbers. So right there, you're ahead. So let's go ahead and click OK and see what happens. And actually, I'm going to only show these 3 parts. So it created part 5, which is the first set of spokes. Part 6 is the second set of spokes, and part 7 is the line connecting the 2 centroids here. And the element type is totally up to you. You can say these are rigid elements, parts 5 and 6. And the reason why they have to be 2 different parts, by the way, is because rigid elements all have to share that 1 point. And this could be beam, and it would be up to you whether to set the diameter equal to the diameter of the hole or something different. That's totally up to you.
Yeah, as you can see on the bottom of the tree, we have the meshes option, and the centroid mesh that you just created is considered a mesh, and it is editable, which means if you wanted to change the surfaces that it is trying to connect and maybe change it to an edge, you can do that after the fact. So that's one thing I wanted to add. And the second thing I wanted to add is that the naming is also pretty important. We named parts 5, 6, and 7 the same name as the centroid mesh that controls them. So as you can see, the parts 5, 6, and 7 automatically got named centroid mesh 1 because the centroid mesh 1 is what created them and what controls them. So you can get a visual associativity between them as well as mesh associativity.
Mm-hmm. And of course, in a simple model like that, that's not crucial. But if you have many parts and you've used the Centroid Creator many times, it's nice to be able to associate which parts are generated by which Centroid Creator.
Yeah. Let's move on to our next improvement from the PowerPoint. The next improvement that we worked on is the ability to show our nodal mesh refinements in the browser tree, much like the Centroid Creator we were looking at a second ago. This was a pretty common request from our user base. They often use refinement points for surfaces, edges, as well as points in order to get a better quality mesh in localized areas. Whenever they created surface or edge-based refinements, those line items automatically got added to the browser. Nodal-based refinement points never were included in the browser, and therefore it was very difficult to select and edit or delete them from the file. Now we added them in the software in the browser, much like we do for surface and edge-based refinements, which makes it a lot easier to select, edit, and modify them. So here we're looking at a wheel design, and as you can see, we have a refinement point under the meshes on the left-hand side in the browser. And let's zoom in and show that. So looks like this refinement point, which is represented by the black dot, is impacting a very small refinement radius, which is represented by the orange-looking sphere. And if we wanted to edit that, in the past we would have to select it from the canvas only. And sometimes it gets difficult to select things from the canvas. It's always better to have a list of things we can edit from the tree. So that's what we did this year.
And they're grouped. So this refinement point operation was just selecting one vertex and defining a refinement point on it, and that appeared under this heading here. There's only one refinement point. have we selected multiple points, they would also appear under one heading.
Let's go ahead and demonstrate maybe selecting 2 or 3 more.
Actually, yeah, I want to show you a nice way to select refinement point that I've used since we're on the topic. What I sometimes find very useful to do is go and select edges. And select an edge, then select related vertices, and then do refinement points on that. Add refinement points. Okay, so it says the estimated mesh size here is 0.008, so let's say it's 0.1 radius and a mesh size of 0.004. Okay. Ooh, maybe okay, so obviously I made my radius
very large.
Very large. Okay, that's perfect example. All right, so let's go here. First of all, you can see that they're all grouped under this heading here. So I can just right click on the heading and edit them all at the same time. Or of course you can select individual ones. But in this case, say, okay, well, I really want it 001, let's say. Or maybe, yeah, 0.8, I think is what I wanted. Let's see what happens here. Okay, maybe 0.008 then. And here we go. That's really what I wanted. And you can see how it generated all these. Oh, it's very easily selectable and editable without having to select anything on the canvas or the model itself. It's all in the tree grouped nicely for you, where you can select them.
Yeah, without this functionality in the 2016 release and before, you had to select them from the canvas to edit them, or you had to go to the mesh dialog in the ribbon, and all the way to the right you had the specify nodes dialog, which is where everything still gets stored, and you would have to know exactly which specific mesh refinement ID you were trying to edit, which was becoming very, very difficult to use as the number of refinement points you were adding to the software increases.
Yeah, if you had a dozen, that's okay, but if you had hundreds, this big table was not useful unless you wanted to get rid of all of them, which is hitting the clear button.
That's right.
Otherwise, that was pretty much the only thing it was useful for, is to clear them all. Otherwise, to edit them, you would have to do them individually, which was painful. There was no way to like copy or select multiple rows and change them. You had to do them individually. So this is a really very good improvement for those of you who use refinement points often.
All right, let's move to our next improvement around meshing usability and meshing technology. So the next thing that we did is we added the capability to create unmatched meshes with one click. Simulation mechanical solvers historically relied on and really needed a matched mesh in order to consider multiple parts to be in either bonded or surface contact for different analysis types. Many years ago, when we started adding functionality for nonlinear transient analyses, the ones that we all know as MES today, we realized that unmatched meshes is actually a necessity when we're dealing with surface contact. However, creating unmatched meshes within simulation mechanical was never easy. We always had to do a lot of tricks and multiple clicks to get unmatched meshes between parts that we wanted to be in surface contact for MES, which made the MES setups that much more difficult. With the introduction of the Nastran solvers, which doesn't necessarily need a matched mesh between parts for bonded or surface contact for linear or nonlinear analyses, the necessity to create unmatched meshes with ease really increased for us. So in the 2017 release, we have a single checkbox in the meshing dialog that will create unmatched meshes with ease. So let's demonstrate that.
So let's open a model to demonstrate that. It's that model that was shown in the slide, actually. Okay, so let's go to default.
Maybe let's change the visualization to a color by surface so that the greenish hue goes away. There we go.
Okay, nice. All right. So we'll go to design scenario 1, which is the default, which is to match the meshes. And what that means, we'll go again to surface here, and we'll look at the mesh between the two parts, and you can see that it matches the nodes at the interface between the two parts. That is the default, and that's probably good for most models, except that if you don't, like Sualp mentioned, don't want the matches to mesh for one reason or another, now we have, if you go to mesh, 3D mesh settings, and by the way, this dialog here has changed, and we go to, actually it's right on this very first screen, we uncheck the create match meshes between parts. And if we generate this mesh, actually I don't want to do that. We can look at the second design scenario where we've already done that. And you can see that each surface has its own mesh and they are not matched.
So there's multiple advantages of creating a matched mesh versus unmatched mesh. If you are creating a matched mesh, the solvers will typically be better off trying to give you a more accurate results when it comes to the contact regions. However, the quality of elements that you will get when you create an unmatched mesh will typically be better. So there are advantages and disadvantages to both. The other thing that I want to highlight here is you can see that the cylinder has a much better looking mesh when we create an unmatched mesh because it can capture that curvature much better, and therefore it can capture the volume that that cylinder presents much better, and the moment of inertia and inertial effects that it will have will be better captured as well. So I highly recommend maybe playing with those options and taking a look at your results to figure out what kind of mesh better suits your needs. But the one thing I will say about matched mesh versus unmatched mesh is the fact that unmatched mesh is much easier for the mesher to create. So if you're having trouble meshing your assemblies using the default settings, the first thing I recommend for you to work on is simply creating an unmatched mesh, which will increase your chances of getting a successful mesh.
And if you wanted the surfaces to be bonded, you can of course use the smart bonding.
For simulation mechanical.
For simulation mechanical. For Nastran, it's a default. Yeah, it's unnecessary to have. You don't need that extra step to say, hey, use smart bonding.
Now let's zoom out a little bit and take a look at what's happening on this fillet right here. So maybe put it in some sort of a view we can better look. Maybe put this this top cube or something. There you go. So we have a fillet over here on the model. And what we're trying to show here is what happens to our meshes when we use our default mesh style. So our default mesh style for the past 10, 20 years for surface meshing has been using a technique called advancing front, which means our surface mesher starts meshing a given surface from the edges of that surface and starts going into the center of that surface. And whenever we have that type of a technique, sometimes we represent a fillet like this using multiple triangles, which doesn't really capture that curvature properly.
And actually we can see something not quite as dramatic, but very familiar on the mesh on this cylindrical or circular surface. You might have wondered in the past, saying, okay, this is a circular surface. Why am I getting, this triangular element here? Why do I have this triangular element here and not maybe diametrically opposite? right? Why does it not look as uniform as one would think, given the uniformity of the circle?
That's right. So to address some of these concerns, we decided to invest heavily on an entirely new type of surface mesher. So this new surface mesher is another option for you to try if the default mesh doesn't look as good as you want it to, or if the default mesh is not successful, or if the default mesh doesn't give the results that you think you should be getting. And this new technique is called Delaunay plus Advancing Front technique. And this is available in the meshing options under the Surface Mesh tab. It's the option all the way at the bottom. It is not on by default. It is definitely an option because this is our first year introducing this technique, and therefore we wanted you to be able to continue getting the same results that you were getting before with the default measures. But if you wanted to, you could activate this new technique and hopefully see different and hopefully better results. So we actually did all of that in the third design scenario for the same model. We created an unmatched mesh using the Delaunay plus Advancing Front measure. And here, what we are looking at is, Marwan is showing that that's what we used in this scenario. What you're looking at is a much more uniform looking mesh for both the fillet surface that we highlighted as well as the circular surfaces on the edges of a cylinder. So let's take a look at it once again using the color of surface. And as you can see, the circular surface has a very symmetrical mesh, and in fact we have trained the software to recognize certain very common geometric shapes and always mesh them using a similar style. So anytime you use this technique, you will always get a rectangular core and a circular outer surface whenever you're meshing circular surfaces. So that's why you see the exact same mesh basically on the other side of that same cylindrical object. And this is true also for fillet-looking objects as well. So when we look at the all four fillets, we will always see the same rectangular mesh around those circles, around those edges rather. So Marwan's showing one over there on the bottom left, but all the fillets should have the same look and feel without the introduction of the triangular elements. As much as possible, this option will try to give us the most uniform looking rectangular surface mesh. And as we all know, a good surface mesh will yield a good solid mesh at the end of the day. All right, let's move on to our next improvement. And looks like we're almost over with the entire hour, so we'll hurry up and talk about our next enhancement, which is around stress linearization in the next minute. Could you maybe just, let's talk through it on the PowerPoint.
Oh, okay.
7.
All right.
There you go.
Yeah.
So the next improvement that we worked on was a complete rewrite for our stress linearization environment. What we're looking at here are two images. The image on the left shows the stress linearization environment from 2016, and the image on the right is the 2017 stress linearization environment. The 2016 environment was outside of our simulation mechanical software. Whenever you accessed stress linearization, it would bring up an entire new user interface that wasn't in par with our current interface. And it was written in some old technology and therefore had many limitations. So in the 2017 release, we have embedded the ability to do a stress linearization directly in our results post-processor within simulation mechanical. So that's the first bullet point, that it is embedded. The second bullet point is the fact that we now can do a stress linearization for models that contain mid-side nodes. The next one is the fact that we can now also do stress linearization for both 3D models as well as 2D plate models. We can do stress linearization for linear or nonlinear models, whereas in the past it was limited to linear static stress only. Now we can do stress linearization for any type of analysis that produces a stress result. We have some additional controls where we can control the location of the first point and the last point, and that it doesn't have to be based on existing coordinates. We can pick any coordinate in space. We can also control the divisions on the stress classification line and control how many stress classification line points that we want, which gives us better accuracy in results. In addition, the stress linearization tool gives you additional feedback. Now, if you make an error during your input, we give you warnings and error messages in plain English that explains what you may have done incorrectly and how you can fix it. Also, we added a button to export the results not only to a comma-separated value or Excel, but directly into the report HTML report environment, very similar to what you have seen Marwan demonstrate with the additional results output. Exactly. If you want to find out more about stress linearization, what it's used for, and some of the improvements, feel free to tune in to SimTV, where we will post some videos around all the improvements included in 2017 for stress linearization.
Yeah, I think the fact that you can do 2D now is very important, because oftentimes you want to do a 2D model to be able to get more accurate results faster by throwing a finer mesh, but then if you can't do stress linearization, then you're not going to be able to do that. Now that opens a whole new door for you. I think that's...
And then the final improvement that we did is the fact that we can now display contact pressure results for analyses that you have run using the Nastran solvers. Once again, this improvement is only if you have run your analysis using the Nastran solvers and you have certain contact settings set up. You can be looking at the contact pressure as a color contour. So this is our first improvement in contact pressure. I feel like more to come in this area in the coming years. So you can look at contact pressures, XY tractions, and contact status directly in the canvas. And this concludes our PowerPoints and in-software demonstration of all the new features of Autodesk Simulation Mechanical 2017. I'd like to thank you all for joining and open it up for any questions that you may have. And I see that there are some messages popping up in the meeting, so we'll see if we can read and answer some of those questions. I'll read it out loud. How can we find the reaction forces between different parts in an assembly? The next one is, I love the changes in the Inquire results and mesh refinement. Thank you for those improvements. The next one is match versus unmatched mesh. Is it true to unmatched mesh works better with Nastran solvers? And then the final is, how is the mesh affected if the mesh matching is turned on? So it looks like a lot of questions around mesh matching.
Yeah. Well, I'll take that last one. How is the mesh affected if mesh matching is turned on? Well, that's the way we've always done it, really, is with the mesh matching turned on. And how it affects it, sometimes, I don't know if you've noticed with that model, it forced some of the mesh lines on the whole part, not on the shaft part, to kind of be slanted or not quite as nice. So it's really going to force them to match, which will maybe generate some elements with maybe high aspect ratios. And you can see that very clearly on the mesh itself, on the outside. So if you can do without mesh matching, then typically you would get a nicer mesh.
So I'll answer the question just about that, which was the match versus unmatched mesh. Isn't true that the unmatched mesh works better with Nastran Solver. So I've actually done quite a few tests in the past couple weeks about that. So I think it's a good time to answer this question. Whenever you do an unmatched mesh with SimMech or Nastran solvers, it really doesn't matter, you will end up creating a mesh that has a lot less elements. So that means the problem size will be much smaller. So typically, an unmatched mesh will solve much faster. But that doesn't mean you'll get the same accuracy or something that's more accurate than the matched mesh accuracy. Typically, you will get a better accuracy out of a meshed match when you're dealing with an assembly. So I think the question comes back to you. Do you want faster results or more accurate results? And if you want more accurate results and use an unmatched mesh, I recommend always doing a H-adaptive study and do a mesh convergence study to see if your results are accurate with an unmatched mesh by changing your mesh size and getting smaller and smaller meshes. And this is really true for any type of mesh matching or unmatched meshes. You always want to make sure that you are getting accurate results, or rather precise results. I don't mean to say accurate results. I mean to say precise results by doing a H-adaptive mesh study.
But first question, how can we find reaction forces between different parts in an assembly? I think that was the last slide, right? Using the Nastran solver, that gives you reaction forces between parts.
Contact pressure.
Contact pressure.
That's right.
Yeah.
And I think we got a couple other questions while we were answering these. So the next question I'll read out loud. It says, do you think in the future you'll be going more to the Nastran solvers being default and moving away from the current solvers? So this kind of gets into the future discussion, which we're not really super comfortable doing in a call like this, Paul. But what I'll say is we will probably continue to serve both the simulation mechanical legacy solvers as well as the Nastran solvers with simulation mechanical. As you may be aware, we have certain projects on a Autodesk Labs called Project Arrow. So if you're interested in how we're taking better advantage of some of the Nastran solvers with a completely different interface, I would recommend that you take a look at that project and see some of the things that we're working on for the future. And the next question, let's see, is...
Beam visualization, 3D beam visualization in the FEA editor environment. That is still not the case. You still have to check the model and look at it in the results environment to see the 3D visualization of beam elements. I think we got another one here from Steve. Unmatched mesh on an assembly requires the use of smart bonding in SimMech, correct? Yes, it is correct. Here are the conditions for use of the smart bonding, yes.
So I think Steve...
it's a comment, I think, more so than a question.
Well, maybe. I'm not sure. So let me see if I understand you correctly, Steve. You asked if to use the unmatched mesh on an assembly and use simulation mechanical's legacy solvers, that we have to use smart bonding. That is the case for linear analyses, correct. But in a nonlinear analysis, such as MES, you can use that unmatched mesh and use what's called tied contact. So that's an option that not many people know about, but that's also available. And I think possibly what you're asking for when you say, please review the conditions for use of smart bonding, I think you're asking for some background on how to use it and when to use it. I'd say probably your best bet is to take a look at some of our help documentation, and if you still have questions, you feel free to contact tech support on that. I don't think we want to go through all those conditions in this call.
Yeah, I think with no more questions coming in and us running over our time here, looks like it's time to wrap this up. Again, thank you everyone for attending, and we're excited about all these changes, and we encourage you to explore them and take advantage of them. And if you have any questions that come up during the use, you know how to reach us, or we hope you do. And we are here to help you.
Yeah. And thank you for your time once again. And we hope to talk to you soon in another upcoming webinar. Thanks, guys.
Thank
Bye.
you.